We are arrived. The proof of correctness. Let's prove that sort, insertion sort, is an actual sort. So if you recall, is a sorting algorithm is a conjunction, right? A function f is a sorting algorithm if on the one hand it produces permutations, and on the other hand it produces sorted lists. So we're going to use this sort of like split structuring of the property we care about, of the specification of a sorting algorithm, to structure our proof that our function is in fact a sorting algorithm. So we'll prove first using two lemmas that our sort is produces permutations. First, by proving a lemma that says insert sorted is just as good as cons in terms of producing permutations, and then second, proving that a list is a permutation of its sorting. Right. These two together show that sort produces permutations. You'll prove these using sort of more or less conventional inductions, but you'll need to use lemmas that we've already shown. Okay, that's the first part. The next part is proving that the function is sorted. So the harder proof here is to say that, look, if a list L is sorted, then so is inserting some A into L, or A is some natural number, right? LEB spec is going to be super handy. It's going to give you information that you need to know. Um, uh, just another hint, you're not going to need insert sorted perm or sort perm. It's just a straightforward induction right at the beginning. It is tricky, so be ready for that. I think everywhere perm is sort of a related lemma in terms of thinking about how that looks. So I expect to chat about this with y'all on Zulip. This one is much easier. Just not super hard. You'll of course need to use lemmas from before. Now to wrap it all up, you just say, hey, yeah, we got all the parts. Right? That's all it is. So this I think is a really nice structuring of the proof because it lets us see that, like, okay, to show that we're a sorting algorithm, we can sort of like split into two camps, and there's like camp permutation and there's camp sorted, and then we just sort of have to like reassemble the camps um, as necessary at the end. So there's some nice extra lemmas at the end. There's a concept in sorts called stability, which says that, hey, if I have a list and things that are considered equal, they'll stay in the order they were originally in. Stability is not a meaningful concept if you just have numbers, right? Because what's the difference between two numbers? But if you're sorting things based on some index, say sorting people by first name, then it might matter. Like, oh well, if people were in some certain first name order, you would keep them in that original order if two people both had the name Michael or whatever. Right, so stability is an important property to know about. We're not going to talk about it in this setting because we can't really. But there are two other related properties that I think people will be into. One, if a list is sorted, then sort L is just equal to L. Right? If it's already sorted, sort's just not going to do anything, which is related to stability. And then next, that sort of L is just sort of L, right? Sort is idempotent. So these are both like meaningful properties that people might like to know about. So one might, if you were optimizing your program, might try to find places where something was accidentally sorted twice in a row, say in one function and then another, and then turn it into just one sort. And this lemma would justify exactly that kind of reasoning. All right, this is an optional exercise, but I just wanted to show it. I think it's a great one to do, and not too bad, but just extra work, extra practice, in case you don't want it. Okay, one more video coming at you from this, just talking about the sort prime uh, specification of sortedness, and the relationship between sorted and sorted prime. So that's a bunch of optional exercises, but please do watch the video and take a look in any case just to get the ideas in your head. All right, talk to y'all soon.